Team, welcome to 7.6 assignment. I just wanted to mention and encourage you guys to watch these videos prior. If you're feeling extremely lazy, I'm going to do the very, very quick version of what these videos are saying, and it's why I gave you guys this paper. Q is basically if we calculate K before equilibrium. So before like right when we throw all of the ingredients into a reaction, it takes a little while to get to equilibrium, but right away, right at the beginning, you can be like, well, what is the constant value right now? And that's Q. That's big Q. That's basically K at a specific point in time. And so if Q is greater than K, then the reaction it's going to shift towards the reactants, okay, to the left. If K is bigger than Q, the system is going to shift to the right, which are towards the products. If they're equal to each other, then it's already at equilibrium. And that makes sense. If Q is equal to K, then yeah, they've already reached equilibrium. So Q is if we do the calculation for K, which is products over reactants, before we've reached equilibrium. And if you want to think about it that way, you could say after, like, well, no, it's always before. It's always before equilibrium. So, because once you've reached equilibrium, it just stays constant. There's no change. The slope is there's just no change at all. And so before we reach K, you can do this calculation of products over reactants, and it gives you this Q value. Okay, now beat that dead horse. Let's head over and take a look at 7.6. All right, 7.6, we've got this carbon monoxide bromine gas becoming this carbon oxide bromine combination. Um, K, they gave us this K value of 1.4 times 10 to the negative fifth, relatively small, okay? And I would guess that if it's that small, it's going to probably shift towards the reactants. But we can't assume that right now because we need to calculate a Q. For the reaction system represented above, the initial partial pressures are bump, 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 bump. They give us all right there. As the system approaches equilibrium, which of the following will occur and why? And the reason why we can't do the K calculation, we have to call it Q, is because we are approaching equilibrium. Okay, so because it says this word approaching equilibrium, we have to calculate Q. Okay, which is the same thing. It's still reactants over products. So let me see if I can do that work right over here, out here in this empty space, if that'll work. There we go. So we got K. Oh no, that's not going to work. Let's just bring that over just a little, and we're going to go K is equal to products, which if I look over here is 0.01. Okay, divided by reactants, which is 2.0 times, I don't see any coefficients, so that's really, really nice, times 2.5, there we go. Okay, so I calculate this out, 0.01 divided by 2 times 2.5 on the bottom. My K value comes out to be, K is equal to 0.002. Now, it's interesting, I was showing my work earlier, and I actually wrote this incorrectly. This is Q because we haven't reached equilibrium yet. Okay, so my Q value is 0.002, or 2 times 10 to the negative third. This is 1.4 times 10 to the negative fifth. K is significantly smaller. Okay, and let me see if I can write that here. So I have Q is greater than K. And if I go back and look at my at the information, okay, let me see if I'm recording here. Yeah. So if Q is greater than K, the reactants are favored. It's going to shift towards the left. Let's head back over there. Let's go back over. Okay. So if we're shifting to the left, there's going to be more of the reactants. more carbon monoxide and bromine gas will form because Q is less than K. That can't be right. Okay, get that junk out of here. Nope. Get that out of here. And I'll actually switch. I'm liking the color red a little bit better. More carbon monoxide and bromine will form because Q is greater than K. That looks like the one. Okay, I'll just put a little dot there. No, that can't be it. Okay, nope, not possible. It's got to be B right there. It's got to be B. So, all right, number 1 is done. Let's go down to number 2. Okay, we've got this. We've got a K value that's small again. At high temperatures, this decomposes. Okay, and it's all gases. Okay, so equation of sample gases injected into a rigid vacuum. The initial concentrations of the gases are listed below. Okay, and I am just going to do a simple Q calculation with what they've given me. Which of the following best predicts how the total pressure in the vessel will change as the system moves toward? Once again, we've got this moves toward equilibrium. Because we're moving towards, this has to be a Q calculation, which Q is equal to, okay, products over reactants, which, let me see, I'll just cheat and start typing in here. Okay, so my products are carbon monoxide, 0.3, okay, and that's going to be squared, okay, because, and the reason why is we have a coefficient on that one, and that's going to be times, okay, oxygen, which is 0.3, actually, okay, and all that is going to be divided by, and what's on the bottom, because it's products over reactants, is carbon dioxide, which is 1.0, okay? And 1.0 is actually squared as well because it has that coefficient. So now that I do that, okay, my Q value, oh, and it's got to be uppercase Q, okay? Q is equal to 0.027. Okay, that's my constant value as we approach equilibrium. Now let me take a look back at my notes. My notes say, okay, I have this 0.027 compared to a point, and so this would be 2.7 times 10 to the negative 2. Q is greater, Q once again is greater than K. And so if Q is greater than K, reaction shifts to the left, towards the products. Sorry, to the left is towards the reactants, towards carbon dioxide. Which of the following best predicts how the total pressure in the vessel will change as the system moves towards equilibrium? The total pressure will increase, the total pressure will decrease, stay the same. Okay, now let me just scroll up here and show you guys something. On the reactant side, how many moles of stuff do we have? We have a total of 2 moles over here, okay? And you can see that because of these coefficients. Over here, I have a total of 2 moles, okay, plus 1 mole of oxygen. So altogether, in the product side, there's 3 moles. On the reactant side, there's 2 moles. And because it's gas, which is going to have more pressure? 3 moles of something is going to create more collisions, more pressure than just 2 moles of something. Think about siblings. You put 2 siblings into a room together. Is it less chaotic or more chaotic than when there's 3 siblings in the same room together? This is more chaotic, more pressure, so this is less pressure. And if the reaction, and we just established that the reaction is going to shift this direction because Q, okay, because Q is greater than K. And if it's going to shift this direction, and my arrow got away from me there, sorry team, it's shifting to the left, that means there's only going to be 2 moles instead of 3 moles. The pressure is going to decrease. Okay? There's a few different ways you can explain that. That's what makes the most sense to me. So number 2, total pressure decreases. We're going towards 2 moles of carbon dioxide rather than the 3 moles on the right. Okay, number 3 for 7.6. Here we go. Ooh, I did an ice table. Did I end up using that ice table? Because that ice table is pretty intense. Here, let me just take a quick look-see here. I was trying to see why I got it wrong the first time, and it was because I switched the reactants and the products. Okay, so once again, when we're calculating Q, when we're calculating K, when we're doing these calculations, it is always here for these Unit 7, products over reactants. And I made that mistake, and I lost a little bit of time tonight out of my life because I did that. Okay, so Q, okay, let's just read the question again. So nice 1 liter container, so moles divided by liters, that means that this is my molarity, okay? And our K value at the end. So they gave us our molarity and they gave us our K value. So let's see here. Did I use an approximation value? I'm trying to think of what if I make sure that I didn't take a shortcut, because if I did, that would be awkward for everybody. Okay. No, I didn't take a shortcut. I just assumed, I just assumed that, like, hey, this is what they gave us, and I calculated Q immediately when we dropped it into the container. Okay, that was what I ended up doing. So let's calculate Q as we drop this into the container, 0.4 moles of each one of these gases, or a 0.4 molar, or concentration. So we have 0.4. Oh, good heck. Products, and that would be N2, 0.4. Let me just establish up here really quick. So they're saying that we drop 0.4 of each one of these, and we drop them in all at the same time. And I'm just going to show you guys that work here so that you guys can see it. 0.4. So I drop this in all at the same time, and I'm going to calculate Q the moment I drop them all in there. Okay, so this is going to be products over reactants. So that first one's going to be N2. There it is. Now the second one is going to be H2, and I'm going to be let's do this in parentheses, 0.4. Okay, but what's different about H2? It's to the power of 3 because it has that coefficient. Now let's grab one of these trusty dusty lines here. Okay, put it underneath. Oh boy, sometimes this is a little awkward. Thanks for bearing with me, team. There we go. Okay, and now let's get another text box to do the bottom of this problem. Okay, over reactants, and my reactants value is 0.4, okay, to the exponent, okay, of 2 and squared. And you guys know the reason why, because of the coefficient. Okay, so if I type all of that in, my Q value comes out to 0.16. So now I've got to compare my K versus my Q. My Q is 0.16, my K value is 0.62. In this case, K is greater than Q. And so I go back and take a look at the cheat sheet that Mr. Anderson provided. It is, if K is greater than Q, the reaction favors the products, causing the system to shift to the right. Okay, so let's head back over. So if I'm going to shift towards the products, let me just draw that line, shifting towards the products. Let's see how that informs my reaction. At equilibrium, which of the gases will have the highest concentration? So that means it's got to be either, and I'll switch to the color green just for dramatic effect here. It's got to be either nitrogen gas or hydrogen gas. Okay, and it's pretty easy for me to determine which one of these is going to be the higher concentration. It's going to be hydrogen gas because there's 3 moles of it, okay? Because we have 3 moles of the hydrogen gas as my coefficient, that concentration is going to be a lot stronger than nitrogen. So, and yeah, if you guys need more information or clarification on that, feel free to talk to me about it. Okay, we're on number 4. We made it, team. We're all the way to the end here. I'm going to zoom out just a hair, try to give us a little more room, take a look at things here. We've got x squared, and this is just representing our equation. They gave us k value. The equation represents the synthesis of x, y, and that looks like these guys right here, x, y. Those are the money makers. That's the products right there. The diagram below depicts a mixture of 3 species. So we've got all 3 species represented. There's our YY. There's our XX. Okay. Each molecule represents, in the diagram, represents 1 mole of the compound. So technically, here in the drawing, there are 2 moles, okay, of XY. And 1, 2, 3, 4, 5 moles of YY. Okay, so let me draw a little 5 there. 5 moles of YY, and there's only 1 mole of XX. 1 mole. Okay. In which direction will the reaction proceed to reach equilibrium at this temperature? Now, the nice thing is they gave this all to us. When they do this, guys, this is such a solid hint in a 1 liter rigid vessel. Okay, if it's a 1 liter vessel, and it's that, and they've given us moles like they did here. I counted there. That was like, hey, represents 1 mole. So I just counted them up. I wrote them down. And now I can do a quick Q calculation. Okay? Because 5 divided by 1 is just 5 molar. Okay? So the concentration for this is 5. The concentration for this is 1. The concentration for this is 2. But we got to remember that coefficient. So let's do that really quick and see where we end up. Okay, so let's grab this, and I apologize, team. I know it must be painful watching me type all this out. Products, which is 2. Good Lord. To the exponent 2. That's funny. I actually made a mistake on my work that I just caught. But because the numbers still worked out, I got lucky. But yeah, it's not important for you guys to know right now. I don't want to make that same mistake in front of you and have you guys do it now or later. All right, so we've got 2 to the power of 2, which comes out to 4. Right? So my Q value here is equal to 4 divided by 5. Okay? And if 4 divided by 5 comes out to 0.8, that's my Q value. My K value is 0.15. So again, comparing Q and K, Q is greater than K. And if Q is greater than K, let me just double check my notes. Go back to those notes, Mr. Anderson. Q is greater than K, the reaction favors the reactants, shifting the system to the left. So let's shift to the left on this one. Zooming out a little bit, okay? And if we shift to the left and we go this direction, in which direction will the reaction proceed to reach equilibrium? Okay, the reaction will proceed towards the reactants, towards the product. The reaction will not proceed in any direction. There will not enough information. We know, because we did the calculation and Q is greater than K, it's going to go to the left. You guys just confirmed that. So anyway, thank you so much, team. It's been a pleasure. Hopefully you were able to watch this a little bit faster on one of the faster speeds, and that it matched your guys' answers. Or you just went to the problem that you needed help with. So wish you success. Thank you for everything you guys are doing. I'm proud of you. Keep up the good work.